people see the guidelines and they may think the guidelines kind of come out of nowhere. Actually, the guidelines come from a lot from the periodic table. So if you don't want to memorize the guidelines, there's actually kind of an easy way to remember which ones are which. So the oxidation states make the assumption that we have a Bohr model, which means that we want to completely empty or fill the shell of the atom we're interested in. So if we're trying to completely fill a shell of an atom, meaning it's the more electronegative element, it's going to take electrons, we want to get to the next noble gas up. So if we look at the periodic table, up here on the top right, we've got the halogens. Now the halogens are one electron short of being a noble gas. So things like fluorine, chlorine, bromine, and iodine, if they just gain one electron, will have the same configurations as the next noble gas over. So this is why we have the guideline that if these are the more electronegative elements, they're going to take a -1 charge. If we move over, oxygen, sulfur, selenium, tellurium. These elements are 2 electrons away from being in the noble gas configuration. And because of that, if they are the more electronegative element, they're going to take 2 additional electrons to get a -2 charge. Nitrogens, nitrogen, phosphorus, arsenic, antimony, and bismuth. Again, if they're the more electronegative element, they take electrons and they want to take as many to get to the noble gas configuration. So this is going to be 1, 2, 3 electrons. But as you see, we're starting to cross over into the metalloid line, which means we're getting more and more metallic behavior. So this -3 guideline more applies to nitrogen and sometimes phosphorus than it does to something like arsenic or antimony. Now we'll get to the carbon atoms. Carbon, kind of getting close to this line, occasionally be more electronegative, occasionally it won't. Because of that, we don't have a good guideline. If it is the more electronegative element in a pair, though, it's going to take 1, 2, 3, 4 electrons to get to the noble gas configuration. So now we get to the column before carbon. We've got boron, aluminum, gallium, indium. These are actually much more metallic in character than they are non-metallic, which means they want to lose electrons. So boron wants to get back to the helium configuration. Aluminum wants to get back to the neon configuration. Gallium wants to get back to the argon configuration. To do this, they're going to lose both their p and their s electrons. So this is why we'd say boron and aluminum prefer to have +3 oxidation states, is because if they lose their 1p and their 2s electrons, they'll be back to a noble gas configuration. Same thing's true when we cross over here to the column 1, column 2 elements. If we look at something like lithium, sodium, potassium, rubidium, they're 1 electron loss away from being in a noble gas configuration. So if lithium loses an electron, it goes to the helium configuration. If potassium loses an electron, it goes to the argon configuration. And this is why typically the column 1 elements are +1. For the column 2, beryllium, magnesium, calcium, strontium, barium, all of these want to lose 2 electrons because this will put them back into the noble gas configuration. The only things we don't really have guidelines for are these transition metals. And the reasons we don't have guidelines for this is we don't know if they want to completely lose all their s electrons, all their d electrons, or both. So the guidelines we have are really only for the s and p block.